Okay, so today we're going to start talking about a new approximation method that instead of using rectangles is going to use trapezoids. So what I want you guys to do before we get started, well, we'll talk about the situation. So this is Fast and Curious. So Jada is experimenting to see how fast her motorcycle will go. Yesterday we used a left rectangular area approximation method, right rectangular area approximation method, and midpoint to approximate the total distances. Are there other methods? So the new method we're going to talk about is using trapezoids. So I want you guys to answer 1 and 2. Pause the video, and when you're ready, I'm going to get you started on number 3. All right, so number 3 says to use 10 trapezoids of equal subintervals to approximate Jada's distance. We're going to sketch these trapezoids on the graph above. So we're going to sketch them before we actually find their areas. So we're going to do 10 trapezoids with a width of 1. So we're going to start at 0, 0 and draw a little line to there. This is supposed to be a straight line of a trapezoid, and then straight down. Okay, and then we'll do another one to 2. All right, pause the video if you guys need more time to draw your trapezoids. All right, so we are going to find the area of those 10 trapezoids. So before we do that, you guys need to know how to find the area of a trapezoid. All right, and so to find the area of the trapezoid, you add, there's 2 bases, they're the 2 horizontal parts. So base 1 and base 2, divide that by 2, and multiply that by the height. Now these are all, normally a trapezoid, you have 2 horizontal lines that are parallel and then some sides that come down that connect them. Well, our trapezoids are shifted vertically. So I want you guys to know that when we're doing these, this is base 1, this is base 2, and this is your height. So it's a trapezoid that's propped up vertically. All right, so I am going to start with a little bitty trapezoid right here. Whoops. And to figure out base 1 and base 2, we're going to put the left and right side of each trapezoid into the function, which is t squared. So we're going to square that. So when I put 0 in, is going to be 0 squared, which is 0, plus, and then we're going to put 1 in. 1 squared is 1, divided by 2. That's base 1 plus base 2 divided by 2. And then the height, that height is just 1 unit long. Okay, so that takes care of that first trapezoid. The next one, it won't draw like I want it to. The next one is that one. And so the left side of the trapezoid is 1, so 1 squared is 1, plus, and we put 2 in, 2 squared is 4, divided by 2, times the height of 1. All right, I'm going to do one more with y'all and let you finish it. All right, and then that next trapezoid, you put 2 in. 2 squared is 4. 3 in. 3 squared is 9. Divided by 2 times the height of 1. All right, so you guys finish this. Pause the video. Finish 3 and 4, please. And then go ahead and start it back up when you're ready. Okay, so I have this first page all filled in except number 4. So some advantages and disadvantages I put where finding the areas of rectangles is super easy, but the areas were not very accurate. You had big gaps either above or below the curve. And then trapezoids are definitely going to be more accurate because if you look at what we drew, it covers almost the whole area under the curve. There are a few little gaps, but it covers it really well. And so when I did my 10 trapezoids, I got an area of 335 kilometers. So check your area. If something went wrong, you can fix it. And then it tells us that the left Riemann approximation method gave 285, and then the right gave 385. We got 335. So do you see a relationship between them? All right, so what ends up happening is that the trapezoidal sum is the average of the left Riemann sum and the right. Okay, so let's talk about some important ideas. All right, so let's rewrite how you find the area of a trapezoid. So it's base 1 plus base 2 divided by 2 times the height. All right, now for base 1, we're going to evaluate the function at the left endpoint. For base 2, we're going to evaluate the function at the right endpoint. Right. And then height is technically going to be our width or the change in x. Okay, and then to find the area, under f of x, that's going to be approximately the sum of the trapezoids. Now, even though trapezoidal approximation is better than the rectangle approximation, it's still an estimate, and you do over or underestimate. And the rectangle one all depended on increasing or decreasing. The trapezoidal one depends on the concavity. So if the function is concave down, so I'll draw one concave down. Let me try that again. And we're trying to see if a trapezoid is over or under, so I'm just going to draw a couple of trapezoids. helps, sometimes it helps to make them kind of wide because they are a good approximation. It's hard to see over or under if they're too close to each other. So if you make them kind of wide, you can see when a function is concave down, the trapezoidal approximation is going to be an underestimate. Because we have some gaps that are underneath right here and right here. That areas that's not going to be accounted for. All right, and then if we have concave up, okay, and again, we kind of need to make them wide to be able to see it. Concave up is going to be an overestimate. Okay, so we're going to do a couple of examples. So we're going to approximate the area under a curve of f of x equals 4 natural log of x on the interval from 4 to 10 using 3 trapezoids. All right, so I need to note the width of each trapezoid, or technically the height, or you could say the change in x. And it's the same way we did on the previous lesson. So we subtract the right part of the interval minus the left and divide by 2. Sorry, just kidding. We divide by how many trapezoids we want, or how many subintervals, which in this case is 3. And that is going to give you 6 divided by 3, or 2. Right? And I hope you guys remember what a natural log graph looks like. You may or may not. But it's actually the inverse of the E graph, exponential graph. So anyway, it's going to have a vertical asymptote and it's going to curve like this. And a logarithmic graph is always concave down. All right, so we want to go from 4 to 10. So let's just say 4 is about right here. 10 is about right here. All right, and we want 3 trapezoids that are 2 units wide. So that's going to be 6, and that's going to be 8. All right, and I'm just going to go ahead and draw them because I like to. You technically can do all these problems without doing the drawing. It just helps me to make sure I'm doing the right thing. Like I need to see those 3 trapezoids to make sure I did it like I was supposed to. All right, so let's find our area. So we are going to add the 2 bases together, divide by 2, and we're going to multiply by the height or the width of the trapezoid, which I already know is 2. Okay, so to find this left base, base 1, which I would call that one, I need to take 4 and plug it into my function for x. All right, and then to find this base, I need to take 6 and plug it in. Sorry, I didn't get myself in a frame. I'm just going to rewrite. Okay, so that takes care of this area, this first trapezoid right here. And then I'll go to do the next ones. So for the next one, it would be, this is my base 1. So that's going to be 4 natural log of 6. This is base 2 divided by 2 times the height or width of that trapezoid, which would be 2. So that takes care of that one. All right, and then I'm out of room, but I do have one more to do, so plus. All right, then I have this is base 1, so I put 8 into my function. This is base 2, so I put 10 into my function. Divide by 2, multiply by the height or width of the trapezoid, and that takes care of that one. So I found the area approximation for the area under that curve by plugging it in to the function or doing all that in the calculator. You get 45.725. And it doesn't ask, but because the natural log curve is always concave down, this would technically be an underestimate, even though it didn't ask. I'm going to go ahead and say that. So it's slightly too small. Okay, and then for number 2, Joanna jogs along a straight path for time between 0 and 40 minutes. Joanna's velocity is given by a differentiable function, v of t, measured in meters per minute. Selected values of v of t are given in the table below. We're going to use a trapezoidal sum with 4 subintervals as given on the table to approximate the net distance Joanna jogged between t equals 0 and t equals 40. Now, if you notice, it doesn't say equal subintervals. And on the rectangular and trapezoidal approximation, your subintervals do not have to be equal. You're still doing, like for the rectangles, you're still doing the base times the height. For trapezoids, we're still going to use this trapezoidal formula, but our height or our base, whatever, our width is going to change from trapezoid to trapezoid. So don't think that they have to be equal subintervals, because they don't. And on this one, they're not going to be. So this first trapezoid is going to have a height or change in x of 12. But then this next one only changes by 8. There's change in t, I should say. All right, and then the next trapezoid changes by 4. And then the last one changes by 16. So those are your change in time or your h for each trapezoid. All right, and then if we have meters per minute, and we technically, net distance is going to be meters, we're going to accumulate those areas. When we accumulate the areas under a curve, that's a rate, it gives us a rate of meters per minute that gives us meters. Okay, so now when I'm going to find my area of trapezoids for the first trapezoid, this would be B1, this would be B2. And 12 is the height of that trapezoid. Okay, the next one changes. All right, so for the next trapezoid, this is B1 and this is B2. And then this would be my height, 8. Okay, so you guys finish the other 2 trapezoids on your own, please. All right, so don't let that negative velocity make you start thinking weird things. It just means that she changed direction and started running back where she's in the direction she started from. And so net distance is, we have to subtract that away. So anyway, so this could be plus negative there if you wanted it to be, but I just went ahead and made it minus to make it easier. All right, so that looks like we are going to get a net distance for her of 2,440 meters. Okay, so your assignment for the day is to do this worksheet. And the first part is just determining whether the function is concave up or concave down in that interval. And I want you to try and do that as best you can without a calculator. Now, if you absolutely have to, like, you cannot figure it out, then you can look at the calculator because you need to know that later on in the 5 through 8, because those are the, I think maybe, no, some of the same functions. But the more you can just do out of your head, remembering what a certain graph looks like, the better off you're going to be.